Hello, community! So great that you are back. Yes, we have some brand new AI research and it's just crazy. So let's start here. Welcome to my channel, Discover AI. We have a look at the latest AI research paper. Now, you know what we currently encounter in artificial intelligence. It is what we call the data war. It's a huge wall and you know exactly what it is. We have reached the limit of human annotated data. All the data that were available here by humans, annotated, corrected, and verified by human, more or less are already in the training data of the latest AI machines. Talking about limits, just a very short here reply to my viewers. I just received here a comment and it says here, regarding here this video here of the contextual instantiation of AI persona agents by the University of Stanford. Here, one user recommends here, hey, this line does not appear in the paper. No? This suggests that this prompt acts as a regularization term or the hard constraint of the modal latent space. Where is this line from? So somebody really went here, compared every sentence that I said here to the original paper, and I think this is just great. This is unbelievable if you really go in depth here into my videos. And I just want to give you the solution. Where is it from? Guess what? It is from framing. If you think about a problem, you can find your personal deeper insight. So what I do is, you have here the publication from computer science. This is an archive, and you can go to your AI system and say, hey, this is the PDF. Just give me the 10 most important sentences or give me a textual summary here of the complete PDF, and you would not need my channel for this. You can do this with AI. So what is my added value as a channel? I have different perspectives. I have a different framing. I change here my point of view. And I look at this here from a physics point of view. And I say, hey, let's understand the problem that is here presented and framed in a computer science way from a physical point of view. Or if you like mathematics, I say, okay, let's look at the algorithm that were coded here in computer science now from a mathematical point of view. Let's see where from the mathematical perspective we can find the limits, where we can find approximation, where we can better code implementation, because most of the problem have already been solved in pure mathematics 100 years ago, what people are coding today. And the same is true for physics. And if you are, let's say, a specialist in medicine or in chemistry or in finance or whatever you like, just add your particular vector here so you understand when new knowledge is generated and presented to you only with the glasses of a computer science specialist, my goodness, you can understand it here in so many different other dimensions, and this will accelerate your learning and give you a deeper insight. So this is exactly why you will find in this video also some sentences that are not identical here from the archive preprint from a beautiful research team I'm going to show you, because, yes, I added here a different perspective, different framing. I try to explain the core idea. I don't want just to repeat the most important sentences one by one. Where would be the value? So let's come back to our data wall. Beautiful. So what we have to do, we have to teach AI to teach itself. No, since there's no more human annotated data and humans become much too expensive here for AI development that are just building for trillions of dollar data centers, who could afford here a human labor just going here over the data. So great. AI has to teach itself. Sounds simple. Let's do this. Now, what could go wrong? And we have a brand new framework. It's called the Agent0 framework. And they propose here from Stanford and Salesforce and Chapel University a novel solution here. And now they do it here, let's say, and they say, like children. Children learn playing a game. So let's do here an AI system also play a competitive game. And let's call it Stump the AI Expert. What a beautiful idea. Game theory to further improve the learning modalities of a complex AI system. And here we have it, Agent0, unleashing here a self-evolving agents from zero data via tool integrated reasoning. So authors from UNC, Chapel Hill, Salesforce Research, and Stanford University, they say, hey, we found a new method without any human annotation. The AI system should theoretically learn by itself, and you have here the code available for you. Everything is there. You have here the archive link, everything here, GitHub, Aiming Lab, Agent0. Go there, have fun. Let's come back to the main idea. What are we talking about? So if we have to play a game between two cloned AI systems, so we have one that we call the teacher, and guess what? The other we call the student. But it is now different to the typical imitation learning that we have. The curriculum agent, as we call it now, its goal is not just to generate data, but to generate new problems that reside strictly at the frontier of the other agent capability. You remember that I told you certain AI LLMs are just trained up to a complexity level of 3. They cannot solve complexity level 4 problems. And now is move the goalpost. Go to the absolute fringe of what is theoretically possible to solve at the 3++ level and just go the very tiny next step. So this curriculum agent is incentivized now, and I'll show you how, to propose new tasks that cause uncertainty, a high variance in your answer, and would require external tools, guess what? Python coding tools, to solve this. Actively rewarded for finding the capability frontier. What a beautiful idea. Push it to the absolute limit. And of course, you have to have another agent, the Executor Agent, who has access here to a Python code interpreter or any other tool use. So the student is now able to verify or not verify this, to learn from external data and use the intelligence in the Python code interpreter to come up with new solutions that could be implemented here also in the curriculum agent to further the learning of the curriculum agent. So what we have to do, we have to push the learning over the cliff that exists from complexity level 3 to complexity level 4. What could go wrong? No? Yeah, I ask here Nano Banana Pro here to show you this idea. So on the one side, we have the perfect ecosystem of Python agents, and we have NumPy and Pandas and TensorFlow and everything that you know from decades ago, and we can calculate all of this. And now we have a beautiful cliff. And now the way over the cliff is, hey, let's be creative. No, the AI should find out new ways to learn in a self-learning process. So let's go to the edge of complexity and start the self-training of an AI agent that is inherently the identical agent like the agent doing here with tool use here, the whole Python ecosystems, I think. But now it must be creative and come up with additional intelligence. And you see, two agents, we have a multi-agent system, so we do have a co-evolutionary spiral of learning between those two agents. It sounds great, no? I love it. I went also back to Gemini 3 Pro image preview, our Nano Banana Pro, and I said, hey, give me a visualization. And here we have a dynamic programming, we have a DNA strand here, we have the evolving neural networks, we have new core algorithms. The AI is teaching itself. And this co-evolution of a pair of AI agent sounds just great, you know? As a theoretical physicist, I would just have a very tiny little insignificant question, yeah? Where is this additional intelligence coming from? Because if you train an AI and you say, no human annotated data, okay, so what is the answer? Now, it turns out the solution is rather simple if you follow here the authors by Stanford and Salesforce and UNC. Think about it. We're talking about a probability distribution within our AI systems. You understand that we have here a Markov precision process here at the core of any AI system, and of course probability density fluctuations. So what we do is we look at them. And normally we go here for kind of the peak for the autoregressive LLM. So we see the next token prediction is here somewhere chosen from this region. The probability density is here really high, so this must be the new word, the next token, or whatever. But if we already consumed all of those tokens, and we went further down and down and down, and still no new idea. So what is now this brand new idea? Where is this intelligence coming from? Guess what? From the fringe of knowledge, from the cliff. So you hope that somewhere in this LLM, at the pre-training data, there was also one, let's call it a crazy scientific paper, with a crazy new idea, which is not replicated anywhere, which was just a single little tiny signal here, but that's all there is. So it is hiding somewhere here in the long tail here of our probability distribution, if you calculate here the next token probability. So at the fringe of knowledge, we are now searching for a new solution, for new answers. You see, it can be so simple if you have Nano Pro. Now, just to make sure, no human provides the answer. No human provides a reflection or a guiding or nothing. This is a self-learning AI system to develop further into, remember Odyssey 2001? Hell. So the ground truth is established through tool-integrated reasoning. This is the main idea. So if you just have two AI systems that talk to each other, you have maybe one idiotic system talking to another idiotic AI system. Where should intelligence come from? Now they say, okay, we have whatever communication protocols, let's go with tool-integrated reasoning. We have external world brings in new knowledge. Now you immediately know if we have now the training process and we go with reinforcement learning and we go with a classical PPO from 2017 or with a GRPO, those reasoning tasks, it will not work. And you know exactly why. Because if we are looking for some hard ambitious problems, the standard trust region clipping that we have in a GRPO and a PPO prevents the LLM itself from making here the updates necessary to grasp here a complex new concept. And you might say, why? Well, the reason is simple. We're somewhere here in the long tail. We're looking here for these very singular, crazy ideas that maybe will bring along some new insights. If I just want a short fresh up here on the loss function here for GRPO, you have everything here. Here you have the clipping function, here you have the Kullback-Leibler term, and you know exactly what the Kullback-Leibler term is for now. Acts as a regularization penalty to stabilize the training. And yes, I know one is here collecting or checking, controlling all my sentences. So therefore, yeah, you see, I take a screenshot and yes, of course, it is absolutely according to the publication. Coming back now to this intertwined learning mechanism where we have additional intelligence brought in by tool use. Now, if I start here the complete learning process at iteration 0, the teacher AI proposes here a simple geometric question. Student solves it easily and the teacher receives now no reward because the student AI wasn't challenged at all. We want to go to the edge of knowledge, the fringe of knowledge. Should it be really just theoretically possible? So forced to adapt now to this complexity, the teacher AI begins to construct more complex, let's say, algebraic problems. And now the student AI will fail in the first run. This is perfect. This is exactly what you want, but just at the border. Because we don't have new data to train it. We can just tell the student AI, hey, you are now faced with a problem. What you can do is you can increase here your test time compute. So adjust your weights to master this problem. Maybe you have to run 5 minutes, 10 minutes, half an hour. But find a solution. Just theoretically possible that you could solve it. And the teacher then moves the goalpost again. Now, higher demanding calculus or logical puzzles. So you see, these baby steps, these micro steps, you just want to force the LLM to go into its long tail of its reasoning, and maybe somewhere in the complete internet training data, there was some crazy idea. But you know what's the counterpoint of crazy ideas? No, there could be genius ideas, but it could be also really crazy ideas like flat Earth theories. So you see here the limitations of this process. Anyway, the authors decided, since we cannot go with GRPO or PPO and clipping, we have to introduce a new policy optimization, and they call it an ADPO, Ambiguity-Dynamic Policy Optimization. And guess what? Given here my beautiful visualization by Nano Pro, you know exactly what we're going to do. We dynamically relax here the upper bound of the trust region, and we extend it here in the long tail region here of our probability density distribution. Now, we just have to adopt now the loss function that we have now, not a fixed epsilon, but our upper clip bound epsilon high is now not a constant, like in the GRPO, but a function that is inversely related to the consistency of the job to be done. So if the job is ambitious, so we have a low p hat, the clip widens if you want, allowing here to include more aggressive gradient updates to reward the exploration of new crazy reasoning paths. That's all that there is to it. Otherwise, you see here the loss function, ADPO, but you see the idea is so simple. Don't let you disturb here with a little bit more complex mathematical formula. So talking about a central idea, you might see, so what is the hope that we have? What do we hope for with this new methodology? We hope for that by mathematically targeting new a maximum entropy system, or if you call it uncertainty. In the solver's AI prediction, the curriculum agent is forced to invent progressively more complex logical puzzles, driving at the same time the executor AI to evolve novel reasoning pathways that no human ever annotated before. To go where no one ever went before. Beautiful. Is this realistic? No. But maybe we can go a little bit of these baby steps and do a little bit of improvement. I don't think we have a complete trajectory in front of us where you can go from a complexity level 3 to a complexity level of 100 and we achieve AGI, super hyper intelligence, or whatever you will call it. But how far can we go with this system? Yeah? So I will give you the result. You find all the details in the paper. Have a look at the paper. Maybe read the paper first and come back, and then you will understand here the deeper meaning of this video. So, as the paper says, great, a smaller base LLM can bootstrap its own intelligence significantly without any human in the loop, so we don't have to pay these expensive humans. Everything is done synthetically by artificial intelligence itself. Great. Now, what you guess is our bootstrapping turbo? How far can we bootstrap the intelligence here between two AI agents? I would thought about, now we are limiting ourselves to mathematics. Just to be clear, not complex mathematics, simple mathematics. No? What do you think? If you have an 8 billion LLM, how many percentage points can we increase now the mathematical performance of the system? I would have guessed between 30 and maybe up to 40%. But you know what is reality? If we go with a QN3 8B, the mathematical performance can be improved by up to, in the best case scenario, 18%. So you see how much deeper knowledge is hiding in this long tail of our probability distribution for the next token prediction. Now I can give you a value for QN3. It is less than 18%. But it is 18%, so let's say, come on, let's squeeze out the last piece of performance from a QN3 8B, and let's do this. So, interestingly, so you see we're not anymore narrowing our focus to the highest probability densities, but also to the crazy ideas. But as I told you, those crazy ideas can be real crazy ideas. So the stability of the overall system, you have to be really careful in training the hyperparameter alpha and beta here for the reinforcement learning. Otherwise, you go somewhere completely else. Yeah? So careful in the reinforcement learning. Summary. So I think that complete archive paper shows us that we move a little bit in the AI field from the typical imitation learning, from the teacher-student learning, where we just have the reasoning traces here from the expert-teacher model, and those reasoning traces are more or less just copied into the student model. So copying here, of course, the human thought processes into the student model, we move now to a kind of a 18% limited discovery learning. Discovering new thought processes via verified exploration. But careful, you understand, these new thought processes are not new thought processes. Those are thought processes that were in the pre-training data of copying the human internet. So those were thoughts that are already expressed by some humans in some crazy publication or in some very singular publication, but not the general mainstream. So maybe you could not call it discovery learning, but non-general mainstream learning with the integration of some genius outliers like Albert Einstein in his time. Okay. Just want to tell you here at the very end of this video, this question, where does the additional intelligence come from? An AI is a pattern matching machine, nothing else. It's a machine detecting, projecting, integrating complex pattern beautifully. Of course, you will say, well, if we have an agent that is here the mastermind of the AI code interpreter and has to verify with real mathematical operations in a C++ or a Python environment and verify and confirm here the reasoning process, then all the knowledge here of the code interpreter is the source of the additional knowledge. No? Because the code interpreter will tell this is a valid result or this is an invalid result. So whatever the trained code LLM, or code interpreter, whatever you want to call it, was trained on, it was the human coding knowledge. So now we just, if you want, discover a higher level of human coding knowledge if the code interpreter goes to more complex problems. But the code sequences that the AI code interpreter learned were in the first place human coding sequences. So the intelligence is now transferred just on a higher level to the AI machine. Of course, we talk about tool use in general. So you're not limited to a Python interpreter. Go with any formal solver that you have. Go with Lean 4. If you have access to a supercomputer for quantum field duration, if you work at DAISY, if you work at a global corporation, if you work in biopharmaca, if you work for drug development, you do have your computer programs. Just integrate this into the AI process, but the real decision should be done in your checked, real, formal solver, supercomputer center, and then the result should be brought back into the AI system. So you see, where's this additional intelligence now coming from when we have a self-evolution of an AI system? Yeah, it's not self-evolution in the deeper sense of the word, because the intelligence comes now from the power of Lean 4 or any other formal solver or any other intelligent tool that is just a C++ encoded complexity solver. And of course here in our Python code interpreter as presented here by Stanford and Salesforce Research and UNC. I hope you had a little bit of fun. You see, this is the state of the art where we are currently with self-learning AI multi-agent system. And you see, this was a different framing. I did not use really the exact wording here of the archive paper, but I wanted to give you a little bit of a deeper insight where we are currently with AI research. I hope you enjoyed it. I hope you had a little bit of fun, maybe some deeper insights. It would be great if you subscribe, maybe become a member of the channel. Anyway, I hope to see you in my next video.